Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 5 of Arrow 4080 Finite Elements. Today we're going to be taking a side step. We're going to leave off learning new hand analysis techniques and start learning a few more techniques for developing our NASTRAN decks. So there's going to be some overlap. We're learning how to do springs and truss elements in 1 and 2 dimensions. And now we're going to learn a few more elements to use for our NASTRAN analysis of structures. Let's see how. First, let's take a real fast look at what we've already learned about NASTRAN elements from lecture number 1. We learned about the NASTRAN deck. We saw that comments started with a $sign, and that it's good practice to put your name and the date and things like that up there at the start of your deck. You also can use commands within the deck, the NASTRAN deck, to report this, to solve this, to store this kind of information, but it's good to do it both places so you see it right at the start of your bulk data file. We learned about the executive deck, where we call out what kind of solution we want and a rough estimate of the time and our ending of the executive deck, that CND card. You're going to find when you use pre and post processors like Patran and FEMAP and others that actually they will also generate additional cards, including like the NASTRAN card often, which are used to interface with their program. We're going to always need at least that solution card. It can be called out like static in this case. Solution 101 is the exact same thing, or SE static are old terms. Some finite element codes may not recognize some of the words and may require a number, but many of them require all these. You're going to need that solution, you're going to need the time and the CEND, and most of the other cards are optional. Okay? Got that? You've already used that in Project 1. Okay, next we looked at the case control deck. In that goes from right after the CN down to the begin bulk. We're going to always use the echo card. The echo equals sort in our class unless used otherwise. I want you also to put in a title with our Arrow 4080 project and the project number along with a brief description, and a subtitle that has your name and the date and things like that. You're then going to have information. That title and the subtitle will appear at the top of every page of your output. The labels won't occur, but that also can be used. Subcase information will say for each and every load case what the loading is and what kind of results you want and what the constraints are. What this means is for like subcase 1, when we run that subcase, we're going to need a load. We're going to need to call out the ID of whatever cards have loads. Now you could have force and moment and other cards all with the same ID, and if load equals 1 and those all say 1, then those will all be used by this. If you have load equals 1 and you have one force card that says force of ID is 1 and the next force ID is 2, that means NASTRAN will look at that. It will only use the force with the ID of 1 card for this particular subcase. So you need to give all those different loads, no matter what kind of loads they are, the same ID if they're going to be called out here, or call out their ID here. Okay? So load equals 1. Same thing with the constraints. You need to call out what is going to be the ID of your constraint cards. That means all constraint cards will have the ID that's shown here if you want it to run in the subcase. If you have a SPC card later that has a ID of 2 and you called out only the ID of 1 here in the case control deck, then when it runs this subcase, it will not apply that constraint. Okay. Also, we're going to typically want displacements. We're going to want to know what all the displacements are. We're going to call out SPC forces, which means the forces at all of the single points constraints, any nodes that are constrained. GP forces, which means grid point forces. That gives a grid point force balance that's kind of useful to look at your results. Stresses, if we have areas and forces in our elements, then we can call out the stresses. And forces, we're typically going to want to know what the forces are. So stress and force, we'll call out elemental stresses and forces, while SPC and GP forces will look at the nodes. Okay? So we're going to need cards that indicate our loads, cards that indicate our constraints, and cards that indicate what kind of results we want. We also need the bulk data, the begin bulk card that ends that section. Okay? You can also put a second subcase to run multiple subcases in one model. I kind of discourage that. It's better practice to keep each subcase separate and keep separate runs so you don't get bogged down if you get a problem or a failure. The more loads and constraints the different subcases, the more chance of something failing, and then trying to debug what it was that caused that can be more challenging. So when we look at the bulk data file, that's the stuff down here after the begin bulk and down into and including the end data file. And in this portion, we're going to tell where all of our grid points are. We're going to tell where what our elements are. The elements are generally start with a C for connectivity card, and then have whatever the card is. We're going to have property cards, which generally start with a P, and then whatever the card is. We're going to have material cards, and we're going to have loading cards and constraint cards. Okay? We've used some of these already. Okay, we saw how the grid card worked. Typically, we're going to use the format, the fixed format, or excuse me, free format, where we're going to have grid, comma, the ID, comma. We're generally going to leave field 3 blank, so we'll have another comma, and then we'll put the X, Y, and Z coordinates in global coordinate system. We're typically going to ignore the fields 7 through 10. That's really for advanced use. Okay, and we saw how that work played out in our deck. We also saw the rod card, the C rod card. This is just like the truss element that we've been analyzing by hand, except that a rod can also carry torsion in NASTRAN, while the truss element we've learned to do so far only carries axial load. A rod card only takes axial load in NASTRAN and potentially torsion. We're going to have the C rod card, comma, the element ID, which is an integer, comma, it has to be unique among the elements cards. We're going to have a property card. A lot of different elements can use the same property card, or at least the same kind of element, and comma, and then we're going to have our grid points, one at each end, so we're going to need 2 grid points for that. Here's a typical example of how that works. Now that property card, then, once you have that C-rod, NASTRAN sees your C-rod, it's then going to go look for that property card to know what kind of information to put in for the area and things like that. Okay, here's how that card looks. It then goes and finds the property card, the P-rod card, with the same ID as was called out, and that property card, then that would be P-rod, comma, the property ID, which will be an integer, usually it's just 1, comma, and then the material ID, which often will also be 1, which will be your first material. Then the material card has the modulus elasticity, that kind of information. Then in field 4, we're going to put in the area of that, and if we want it to carry torsion also, we can put in a torsional constant, J. That's not necessarily the polar moment of inertia, that's the torsional constant. So if you have a round section, a round rod, then yes, the torsional constant is the polar moment of inertia. If it's a non-round section, you can put in the torsional constant like we learned in Arrow 3261. C allows us to put in a coefficient to calculate the stresses in the formula shown down there in remark number 3. So if you want to put the radius in for a round rod or the larger thickness for a non-round section and so on, that will allow you to report stresses. And then non-structural mass is the weight per unit length for US units, and basically what it does with that is if you put that in there and have a gravity card that has a way of distributing weight throughout your structure. Okay, typically we're going to ignore this unless I tell you to use that. Okay, blah blah blah. There's no more on the grav card. We'll come back to that if I give you a model where you need to use the grav card. Okay, The material card, one of the most common material cards to use is the MAT1 card. Once again, it's going to be MAT1, comma, and then the material ID, which is generally 1. We're usually going to have just number them from 1 to whatever, however many materials. You're going to have then the Young's modulus and the G and the Poisson's ratio. It's bad practice to put in more than 2 of these. You put 2 of them. Any 2 will suffice. Usually E and G will be best. You can also put E in Poisson's ratio. Rho allows you to put the mass density. It doesn't actually use that for static analysis. A allows you to put in the coefficient of thermal expansion and the reference temperature in field 8 and so on. And then there's some advanced capabilities. Mostly we're going to ignore the stuff, everything after field 5. In fact, you can just put in fields 1 through 4 for most of our models and ignore the rest. Okay? A force card is one of the common loading cards we can use. We've seen this already. It's the force. It's the ID of that card. It's what grid point that force is applied at. We're going to generally leave field 4 blank. We're going to put in a scalar for the magnitude of the force and then a vector to give the orientation of the force, like 0, 1, 0 or something. Okay? The SPC card, we've used that. That basically is a single point constraint. We put in the ID in field 2. We put the grid point where it occurs and the constraint. The constraint is a number where 1 would be like the X, the global X, 2 is the global Y, 3 is the global Z, 4 is moment about the X is constrained, 5 is moment about the Y, 6 is moment about the Z. This also allows you to put in force displacement. We're not going to use this card for that. We'll use a different card for that, and I'll show you that in a moment. We'll basically ignore fields 5 onward. That's for advanced use. Okay? If we sketch our models, let's say we have this is one of the problems from our text. We can quickly, if we wanted to sketch this model, we could do it like this. We define our coordinate system. We would call out grid point 1, usually in a little bubble, a little circle like that neatly. Grid point 2, grid point 3, grid point 4. We don't need to do a lot of measuring, but we put them roughly so it looks like roughly to scale. Element 1, you can use a box for that kind of thing. You want to identify each one. There's element 2, element 3, element 4, and element 5, all identified. Element 6. We then have our single point constraints, right? We have a pin at node 4 and a pin at node 1. Now, while this is only a planar problem, NASTRAN will tend to have singular results if you don't constrain the model in all degrees of freedom. So if there's no element to provide stiffness out of plane, your model will generally crash. So what we will often do is put a constraint to keep it from moving in the out of plane direction, even though there are no forces applied in that direction. It won't affect anything. It'll be like sliding on a frictionless surface. If all of loading is in the plane, then there will be no reason for it to move out of plane, so putting a constraint in the out of plane direction will just allow the purging of those degrees of freedom so your NASTRAN model doesn't blow up. We then can apply our force at the 2 nodes where it's shown, 1,000 points. So that's how that looks. We then can apply our forces at the nodes where the forces are applied, and this is how we would sketch this model here for a finite element. This is how you'll sketch it in your reports also. So if we look at a few more cards, this is SPC1. We already see SPC card, which allows us to put 1 grid points information. If we use the SPC1, we can put in as many nodes as we want and what the constraints are. What we would do is we call it SPC1 and then the grid and then that ID of that card. Then we put the constraints in field 3, which will apply to the node that's identified in 4. If that's all we want, then this card is identical to the SPC card. But we can actually put more and more. We can put a 2nd, 3rd, 4th, 5th, and so on by just continuing on. We can put another grid point and another grid point. In fact, we can list all of the grid points that have the exact same constraint. So what you see here is, in this example, we see SPC1 is given ID 2. It's pinned in the 1, 2, and 3 direction, and that constraint applies to grid point 436, 432, 455, and 460 and 470. Got that? You can also just say G1, put in, like, let's say if you have a node, a structure, and let's see grid points 1, 2, and 3 are all have the same fixity. You could put in what the fixity is in field 3, put in grid point 1 ID, and then write through in field 5, and then write 3 in field 6, and that will constrain all of the grid points from what's shown in field 4 to what's shown in field 6 and everything in between. Got that? This is the way, if we ever do use a displacement, an enforced displacement, then you can do that with the SPC card. It's called SPCD, comma, put your grid point ID or the ID of that constraint. In field 2, in field 3, you put the grid point. Field 4, you put the direction of the constraint. So let's say we're going to constrain our model and it's given an enforced displacement of 0.05 inches in the X direction. That means in field 4, you would put a 1 for the X direction, and then in field 5, you would put what the displacement is, and so on. Okay? You can see here, you can also put a second grid point here and a different constraint. So at the same grid point, you could put another displacement, or you could put a different displacement. Okay? Okay, the CLAS card is used to define springs like we've been analyzing in finite elements. It's going to involve field 1, which calls out CLAS 1, the element ID, the property ID, you'll see the property card off to the right here, the grid point where it starts, and the grid point in field 6 where it ends. And field 5 will tell what direction the stiffness is, so it could be like in the 1 or the 2 or the 3 or whatever direction. Now, you can actually get problems if the element is not aligned. So basically in field 5, we're going to put what direction is this spring in, the X direction, the Y direction, what? And then often what's done in industry is they'll have G1 and G2 be simultaneous, be the same in the same point, two different nodes at the same point, and the only connectivity is that spring, and that allows that spring then to define all the connectivity between those 2 points without getting buggered up. The PLAS card will have the PLAS card, it'll have the property ID and the spring constant. It also allows for a damping constant, which we're mostly not going to use. Okay? CLAS2 is another way of putting both the spring and a spring constant on the same card. On this card, you'd have just the CLAS2, the element ID, and then in field 3, instead of the property card, you just put the spring constant. And then the grid point in 4 and 6 are the 2 grid points, and the direction of the spring in 5. Okay? The CBAR card. CBAR is another. So we're going to use C-rod cards a lot in our class. That's a good element to use for things like stringers and for caps of floor beams and things. The bar is another good element to use. This is a good element to use for frames and for floor beams. So the CBAR card is a very common card. It actually has a lot of capability. We're only going to use a little bit of it, but we're going to have a CBAR. We're going to call out an element ID, the property ID, and the grid points 1 and 2 in fields 4 and 5. Now, the trick with bar elements and many other elements is understanding the properties you're putting in the element and what direction they are. So we're actually gonna, you can see this little figure 1 down here from the NASTRAN manual showing how it's defined, and it's a little bit tricky. And I'm going to show you on the next slide how to make a little toy, a little NASTRAN element orienter like this, so you can see how your thing is defined. You're going to call out grid point 1 and grid point 2, and that's going to define your local coordinate system going from grid point 1 to grid point 2. And then you're going to call out a third grid point, or you're going to call out a vector. So the vector is shown in fields 6, 7, and 8. And 6, 7, 8, you put a vector in, And what that vector will do, so you'll see what you could have done is put in field 6, put a grid point number as that next point. But to put a little vector, so if you have grid point 1 and grid point 2, the vector, if you put in another node, and it's good practice to put one normal to that primary x-axis, what that will do is that will define what your first plane is. So if you draw a line through from grid point 1 to grid point 2 and then up and through that third grid point or that vector, that will define plane number 1 for your properties. So normally we talk about the moment of inertia of a section about its x-axis. Well, what this will do is this will define bending in the plane. So plane 1 is this vertical plane. So if we call out grid point 1, 2, and some point directly above it like this, normal to it, then this plane 1 bending, the first bending moment and the shear will be in this plane, and the bending moment 1 will be in this plane, and bending moment 2 will be in this plane, and shear 2 will be in this plane, okay? You can see that here with end A and end B. I'll show you more about this little toy later. So we've got the grid points 1 and 2 in fields 4 and 5. Then we've got either a third grid point in field 6, or we've got this vector x1, x2, x3, like 0, 0, 1, something like that, or 0, 1, 0. And then the rest of the card, the thing is optional. If you put in components in fields 2 and 3 of the continuation, what that is, those are pin flags. So let's say we put a 4 in there. That means that there's no torsional resistance, a torsional pin. If we put a 5 in there, that's going to be a moment pin. Or a 2 in there, that will be a shear pin, meaning it won't carry any shear. So you can actually put a pin in your element using those. We're typically not going to use those, although we are going to look at an example that uses that in a little bit. Okay? What these W's do is allow you to offset the neutral axis of your section. We're not going to use that at all. That actually has the potential to give you some better results for some problems. It actually is a little dangerous and can screw up your results, and you can be oblivious. So it's better just to leave that all blank. Okay? And you can put preload in there, down there in field 4 of the second continuation card. We're not going to use that either if you were modeling a bolt or something. So here's a little more on the properties. This is the way our moments, our shears and moments are defined. And if you look at this carefully, you see that it's very important to understand how this is aligned. Remember, all the orientation of your bar is just a function of your call out of 3 nodes. 1, GA, GB, and the third node or vector. So it's useful to create a little tool like we're going to see in a minute. I guess we're going to see that on the next slide, this little tool on the next slide. So we can see the CBAR allows us to carry shear and bending in 2 axes. We can offset our neutral axis. We're not going to do that in this class. Our neutral axis and our shear center always coincide with this. That's good enough, because actually if you start messing with that, you're probably going to screw up your numbers. We can apply pins, meaning keep it from transferring a bending moment or something. We're not going to do that in this very much in this class, only for special cases. And it allows some other advanced capability. Okay? This is our PBAR card, where we're putting in properties of the card like the area and the moment of inertia about the 2 axes, the torsional constant, and other things that allow us to recover stresses. Okay, here's more information on how that works, including we can put in a little factor so we can get good shear deflections, which are mostly going to ignore. Okay? All right. This is our property tool, if you make a little tool like this, what I do is I took a nice stiff piece of cardboard. I made the first one of these back when I was a young pup in the early 90s doing finite elements at McDonnell Douglas, which became Boeing. So basically, if you write everything there, you're going to say end A, which is your first node, end B, which is your second node. That's going to define your x coordinate axis. You can see the x coordinate axis here and the y coordinate axis. Once you have 1 and 2, that gives your x-coordinate axis. Once you define either node 3 or that vector, that's going to define the plane in which the moment 1 at end A, and moment 1 at end B, and the shears, which are defined as shown here, are. And that also perpendicular to that defines plane 2, where the second moments are. So it can be very tricky to figure out what direction your loads are and what end they apply to unless you have a little tool like this. And then you can align it with your model if the element is in a weird coordinate system and exactly understand what's going on with those. Okay? The CBEAM card is used commonly in industry by folks that don't know what they're doing because they think it's necessary and because a lot of the pre and post processors generate CBEAM cards. So the CBEAM card allows you to basically have a element where the shear center and the neutral axis don't coincide. Now most of you couldn't handle that when we used to cover that in our 3261 and 3271 classes, and you certainly won't be able to cover it when you're not studying that carefully out there in industry. So basically for most problems it's better to use the simpler CBAR card, which will give less output and it gives you mostly output that you need. The CBEAM will generate a lot of additional output that you're not going to understand, therefore it's a bad card to use. This doesn't mean that the people you talk to will think this is a bad card to use. Most of them are a little ignorant and oblivious, and if they want you to use a different card and if they're superior over you, just go ahead and use what they want you to. But actually it would be better to use the CBAR than the CBEAM for most of our purposes for a number of reasons, mostly for understandability and that kind of thing. If we do use a CBEAM card, we're going to use the PBEAM card, which is like this and is very similar to the CBAR card with a little more capability. Okay, let's look at some examples. So first of all, we need to be able to sketch our final element models. We've talked about this a bit now, so if we have a model like this, we can sketch that out with our coordinate system, elements, right? Each grid point, roughly where they are, and then we'll put in and number our elements wherever they go. Now, what we might also need to do, remember, when we're defining these elements, the local coordinates of these elements is a function of how you call out these cards. Let's say these are rods. If you call out in your NASTRAN deck that your C rod number 3 goes from element 1 to element 4, that means that the X direction, the local X direction, will be in this direction. If you call out that C rod 2 goes from 1 to 3, then that's your local X. If C rod 1 goes from 1 to 2, then that's your local X. Okay? However, let's say that you define C rod 1 as going from 1 to 2, C rod 2 going from 3 to 1, and C rod 3 going from 4 to 1. That defines X coordinates, local X coordinates like this. So you need to be careful with how you call out your elements because that will define what NASTRAN thinks is your local coordinate system, and that means that will define how your results come out. We then see we have pin constraints, so that's going to be 1, 2, 3 at those 3 nodes, and we also can apply our forces. Now, if you're running a NASTRAN model for many of the solvers, if you don't put in a constraint in this is the constraint in all 3 directions, but actually this loading, what NASTRAN sees is no stiffness coming out of plane, so this can flap about like this. So sometimes we'll also put like a 4, 5, 6 at those 3 nodes just to keep NASTRAN from going singular. And because the way this is loaded, that should not affect your results at all because these rods don't have any means of transferring those degrees of freedom up to those elements. Now, if we have, so what we saw here, once again, if we see a structure like this, we should be able to draw and label our NASTRAN structure. If you get a NASTRAN deck like this, you should be able to also quickly sketch your structure. What you do is you go down here and you'd first plot out your grid points. You'd see that's a 0, 0, 0, 20, 0, 0, 20, 15, 0, 0, 15, 0. Then you're going to do your connectivity. You see you have C rod 1, which is using property card 1, which goes from 1 to 2. C rod 2 goes from 1 to 3. C rod 3 goes from 2 to 4. C rod 4 goes from 2 to 3. And C rod 5 goes from 4 to 3. C rod 6 from 1 to 4. That property card, since all of these C rods call it the same property card, that tells what the area is and the non-structural mass. Actually, this has a non-structural mass because some NASTRANs will blow up if you don't put it in there, not because it's going to use it for anything. We've got our material properties, which gives us our modulus, and our G, our shear modulus. We've got constraints. You'll see that we've got a constraint up here in the case control. We're calling SPC equals 1, so both of our constraints, you're using SPC 1. We see at node 1, we've got a constraint in the 1, 2. At node 4, we've got constraints at the 1, 2. And we've got constraints in the 3, 4, 5, 6, which keeps the model from getting crazy at all nodes. See that? Our forces we see, we have at grid point 3 and grid point 2. Both of them are 1,000 in the positive Y. Here's another little example. This looks like a beam with a spring. This means we're going to have two elements. One is going to be a CBAR, and one of them is going to be a spring element. So we'd write our little model like this. We've got our two grid points, and we've got the CBAR going from 1 to 2. We've got our CLAS, which is going from 2, which is at 2, and it's 1,000 pound per inch stiffness in the 2 direction. You see how that works? PBAM is our property card for our beam. We have our material card, we have our forces, and our SPC constraints. Here's another little model, this is continuing. This is now getting the results. So here was our results. I kind of skirted over this. Okay, once we have defined our model from this structure, we see when we run NASTRAN, we're going to get our maximum forces of single point constraint. That's shown right up here, right? We see at node 1, we have no force in the X. We have a force of, what is that? That's 1, 2, 3. That's 2,229 pounds in the Y direction, and no forces. And we've got a moment of, what is that? 53,497 inch kips. See that? Our displacements, we see node 2 has displacements. It has no displacement in the X. It has a vertical displacement of 1.77 inches downward in the Y, and has a rotation at that point as well of 0.01107 radians. If we look at our grid point force balance, we see at grid point 1, we can see that we have a bar with forces. We have a SPC with forces, and those sum up to 0 as they should. This is kind of like doing the method of joints in statics, where you put a joint and then you put all the forces on it. That's what this is kind of doing. At node 2, you see we have a bar, an elast element, and an applied load all at that point, and those all sum up as well, as you can see, and so on. We can then use the output to go and put in our reactions and our shear and moment diagram from those. Okay, here's another little example using the a hinge, which means a pin. In this element, in this model, we'll need 2 CBAR elements, and we'll need to put a pin. We don't want to put a pin in both elements. In one of these elements, we'll put a pin. Here's how it works. So we've got a grid point 1, 2, and 3. You can see here we've got a CBAR, and you can see that we're putting our pin there in number 1. We see we're applying that pin 6. We're taking out the moment about the Z in our first bar. See how that works? And then we've got our PBAR card, our material card, and so on. This gives us displacements like this. You'll see at 1, 2, and 3. You'll see at 2 we have a displacement, and you'll see At 3, we have a... So that is some additional NASTRAN cards to help us keep moving forward in our understanding of NASTRAN. It's fun to practice. You can practice by putting in beams and rods and things from our 3261 class, for instance, or for some of the hand analysis we're going to be doing, you can make a little model and see how that works and check your results. Make sense? Enjoy.